Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello students, welcome again to the TV learning program. I'm teacher Pasco, and today I will be with senior 5 students in unit number 6, learning the chemical properties of carbonyl compounds. In the previous lessons, we discussed some of the preparation methods of carbonyl compounds. And today we will go on with the same unit, but with a new lesson. But before we go deeper in the new lesson, I want you to look at the screen and we read the objectives of our lesson. At the end of this lesson, the chemical properties of carbonyl compounds, the first part, you should be able to describe the reactivity of carbonyl compounds. You will be able to explain why they react like how they react, and why their reactivity is somehow different from the reactivity of other organic compounds. You will also be able to explain what is a nucleophilic addition, and you describe its mechanism. And number 3, you should also be able to describe the condensation reactions of carbonyl compounds. And before we start the new lesson, let us try this revision activity. I'll give you 1 minute to try that one. I remember it very well. It is one of the exercises I gave you in the previous lesson as a homework. So you should be able to do it very fast. How can you synthesize ethanol from ethyl chloride? Good. So we have ethanol, which must be prepared from ethyl chloride. It is not possible for this type of question to do it in a single step. So we should find a way of transforming this original compound in many steps so that we can end up with the compound we want to prepare. We know some of the properties of alcohols. And we know how some of the alcohols, or alcohols in general, can be prepared. And if I'm saying the properties of alcohols, it's because here we have been asked to prepare an aldehyde. And if you remember well, aldehydes can be prepared from alcohols. So is there any way of transforming this halogenoalkane into an alcohol so that we can go on with the alcohol produced and prepare this aldehyde? Yes, there is. So we have CH, 3CH2Cl, which can react with sodium hydroxide dissolved in water, and you reflux to produce an alcohol. The alcohol produced will be CH3CH2OH. This is ethanol plus sodium chloride and H2O. Now we have the alcohol. How can we transform this alcohol into the ethanol we want, CH3CHO? We take the alcohol and oxidize it. Do you remember the oxidizing agent we have to use here? Let us say we use potassium dichromate in acidic medium. What is the other condition? The other condition should be to heat the mixture, but then you have to remember to distill off the product as soon as it is being formed to avoid further oxidation. So we distill off and we produce CH3COH. This is how we can prepare ethanol from ethyl chloride. Now, let me ask you a question. What do you think is the connection, the relationship between this activity and our new lesson, chemical properties of carbonyl compounds? What is the relationship? Here we are showing how carbonyl compounds can be produced. And from the same equation, you can remember how we prepared alcohols from carbonyl compounds. So we have been able to prepare alcohols from carbonyl compounds in a process which is the reverse of this one, of course, because carbonyl compounds have some chemical properties which reflect what we have already covered. So today we will discuss the chemical properties of carbonyl compounds, ketones, and aldehydes, and I'm very sure that some of them, we have already covered them when we are studying alcohols. Reactivity of carbonyl compounds. Before we analyze the different chemical reactions that can be undergone by carbonyl compounds, the aldehydes and ketones, let us see how these carbonyl compounds react generally compared to other classes of organic compounds or the aldehydes and the carbonyl compounds, the aldehydes and the ketones compared. Most of the carbonyl compounds reactions depend on these 3 points. We have a carbon-oxygen double bond. That is their functional group, and because of that functional group and the behavior, the special characteristics it has, the carbonyl compounds will have some of the reactions which are particular to them. And because also of the polarity of the carbon-oxygen bond, some of the reaction will depend on the polarity of this carbon-oxygen bond. When we say polarity, you understand what it means. This carbon is less electronegative, and this oxygen is highly electronegative, 3.5 for oxygen and 2.5 for carbon. The difference is very big, so the bond is highly polar. And then number 3, the presence of the lone pairs on oxygen. If you remember, lone pairs make compounds react in a given way. And because of all this, the carbonyl compounds can undergo many types of reactions, including what? Including, the first one is nucleophilic addition reactions. It is in our objective, what you have to know. And the condensation reactions, reduction reactions, and oxidation reactions. But as I said, today it is the first part. So there is another part in which we will discuss reaction number 3 and number 4. So today we will focus on number 1 and number 2. And where we will need some demonstrations, practical demonstrations, It will be done in the second lesson. So let us start with the nucleophilic addition reactions. And before we start the nucleophilic addition reactions and analyze it in details, let us compare the reactivity of the carbonyl group and the carbon-carbon double bond group. Do you remember where we find this group? Yeah, you do. I'm very sure. This one is found in alkenes. So how do they react? Do they react in the same way, or it is different? It is different because the polarity of the two bonds are different. And though the double bond is present in both groups, they undergo different reactivity due to the polarity of the carbonyl group. And here we have some examples. So you should not be confused and think that because we have some pi electrons and sigma electrons in both groups, they will undergo the same type of reactions. The reactions are quite different because of the polarity of those two groups. So here we have some examples. Only alkenes undergo electrophilic addition reactions. Do we all remember the meaning of electrophilic addition reactions? When we add a molecule across the carbon-carbon double bond, it is added by an electrophilic mechanism. That site, the carbon-carbon double bond, is a site which is rich in electrons. There is a high electron density there. So a species which can attack that site should be an electrophile. Electrophile, which means the one which loves, if I can say, or likes a region of high density of negative charges. So those ones should be like the cations, like a proton, for example. You remember in the hydration of alkenes. So only alkenes with this double bond can undergo electrophilic addition reactions. For the carbonyl compounds, it is not possible. And instead of that electrophilic addition, they will undergo a new type of reaction. The one we are going to discuss very soon, the nucleophilic addition. We will see why it is called nucleophilic and explain. Alkenes cannot be reduced by lithium aluminum hydride because it uses a hydride ion. We know some of the reduction reactions, but for carbonyl compounds, we can use this reducing agent, which cannot be used when we are reducing alkenes. Why? Because the hydride which is used is negative, the hydride ion. So the hydride ion cannot attack the carbon-carbon double bond because here we have a high density of negative charges. This one is also negative, so the attack is not possible. It is totally impossible. So we cannot use that one. Clear. Reactivity of aldehydes compared to that of ketones. In the aldehydes, we have the carbonyl group, as well as in the ketones. But do you think the two carbonyl groups will react in the same way? No, of course, because the groups which are attached to the carbonyl group, they are different. And if they are different, even the polarity of the bond will be different. And when the polarity changes, it will change also how the group will be attacked. And it may also depend on the substance we produce. So we finally find that aldehydes are more reactive than ketones. And that is because in the aldehydes, we have RCOH, while for the ketones, we have RCO and R. So This one is an electron donating group, and this is an electron donating group. But this one is not. So this reduces the partial positive charge which is on the carbon, then changing its reactivity or reducing its reactivity. Now let us start the nucleophilic addition reactions. Here we have the mechanism in general. This is the nucleophile, and here we have a list of some common nucleophiles we can find. This is the cyanide ion. This is the anion from a terminal alkyne. This is a Grignard reagent, which will give us a negative alkyl group. So representing any nucleophile by Nu negative, it attacks the carbon, which is partially positive, and then the bond opens. The double bond opens to create a negative charge on oxygen. The double bond opens like this because oxygen is more electronegative than carbon. And the nucleophile will attack this carbon because it is the one which is less electronegative, and because of that, it will be the one which has a partial positive charge to be attacked by the negative species. So this is generally the mechanism. Reaction with hydrogen cyanide, and the hydrogen cyanide is the first example of the nucleophiles. Remember, a nucleophile is any species, and mainly they are negative, or those ones, molecules containing lone pairs. They are species which will attack a site which is electron deficient. For example, that carbon in the carbonyl group, it has a partial positive charge. So it is electron deficient. And then it can be attacked by any negative species, some negative species which are suitable. And what do we get? To carry out this reaction, we have to use some specific conditions. We carry out the reaction in the presence of potassium cyanide or a base. Why do we use these conditions? It's because HCN is a weak acid. Being weak, it cannot generate enough CN ions, cyanide ions, in the solution. So if you use the OH, the base, it will react with the H positive, increasing the concentration of cyanide ions. This one is ionic. It can also increase the concentration of cyanide ions. And because the HCN is toxic, it's better if you generate it indirectly using like a mixture of sodium cyanide and sulfuric acid. The reaction takes place in two steps: nucleophilic attack and the addition of a proton. Here we have the mechanism. The propanone molecule is reacting with the cyanide ion, and we have the negative part, which is attacking the positive carbon to open the bond towards the oxygen, and we get a negative intermediate. And then the negative intermediate in the next step will use its negative part to take the proton from another molecule of hydrogen cyanide, and then we get what? We get a cyanohydrin. The general name of these compounds containing OH and the cyanide ion is a cyanohydrin. So that is the example. And reaction with a Grignard reagent, with the Grignard reagent we use this alkyl group which is negative. The process is almost the same, except it's actually the same. So the negative part attacks the partial positive carbon, opening the bond, and then we get the negative intermediate, which will attack or attract a hydrogen, a proton, from the mixture. And then you can see that the reacting mixture contains an acid, and we produce an alcohol. Here it should be noted that when we use aldehydes, we produce alcohols, but what kind of alcohols? When we use the simplest aldehyde, we always produce a primary alcohol. When we use a secondary alcohol, other aldehydes, we produce secondary alcohols. And when we use ketones in this reaction, we produce tertiary alcohols. You remember that from the preparation methods of alcohols. Next slide, we have some examples you can try. Complete the following equation, and you state the conditions. It's on the previous slides. It's very simple. And you write the mechanism. This is just for the nucleophilic addition. It's very simple. You can do that. Good. So let us go to the next part of today's lesson, the condensation reactions. And before we go in details, I want to ask you a question. What is a condensation reaction? What do you understand by condensation reaction? Here we have the answer. It is an addition-elimination reaction. So we have two parts, an addition and an elimination in a single reaction. And the reagents we can use, it's ammonia, hydrazine. Hydrazine, its molecular formula is this one, and their derivatives. And the most commonly used derivatives of ammonia, they are amines. You remember the amines from the various homologous series we discussed in Senior 5. And here we have the different reagents we can use, which are derivatives of hydrazine. Hydroxyamine, which when reacted will produce an oxime. Phenohydrazine, which produces phenohydrazone, and 2,4-dinitrophenohydrazine, which will produce a 2,4-dinitrophenohydrazone, and semicarbazide, which will produce a semicarbazone. This compound here is very important as it will be used in the chemical test of aldehydes and ketones when you want to distinguish carbonyl compounds from other organic compounds. We will come back to this in our next lesson. Now let us have a look at what happens. You take your keton, it reacts with an amine, you produce a compound which is called an amine. And how is it done? We have our amine here, which attacks using its lone pair on nitrogen. It attacks the carbon which is partially positive, opening the bond. And we get a species containing a positive charge and negative charge. And the species which is produced will lose its proton, which will be taken by another molecule of the amine, and we produce these two species we have here. And from here, what do we get? We get this oxygen, which attacks the hydrogen and removes it from this quaternary species of the nitrogen. And we produce these two stable compounds. But this is not the final product, as we can see on the next slide. So, because of having the oxygen with the two lone pairs, it also attacks another ion, this one, removing the hydrogen, and the lone pair goes to nitrogen. And then we produce this species, but you can see the oxygen now is positive, what is very unstable. So in this case, the bond breaks, producing a stable water molecule, and here a double bond forms. Nitrogen has a lone pair, and with the positive charge on this carbon, they join to give us a double bond. But as the double bond is formed, we now get a positive charge on the nitrogen. What will be the reason why in the last step? Another molecule of the amine will take this hydrogen, it removes it, and then nitrogen takes its lone pair, giving us an amine and a positive ion. This is the final product of any condensation reaction. We have different compounds that can be used. The hydrazine, if we use this hydrazine, what do we get? CH3COH plus, let us say HN and HNH2. What will be the product? Here we have to show that it's very simple. In a simple way, the oxygen combines with these two hydrogen atoms, giving us CH3CH, a double bond, nitrogen, and NH2 plus H2O. So we have a condensation reaction as it is an addition, but which results in an elimination of a water molecule. And we have other examples you can try. It's very simple. Just point the oxygen to the nitrogen bearing the two hydrogen atoms, and then you remove a water molecule. Here we have the homework you will try. And let me take time to explain what you have to do. Complete the equations below. We have propanone reacting with phenyl-hydrazine. You remember the formula of phenyl-hydrazine? I'm very sure you do. And here we have ethanol reacting with hydroxyamine. You know, this is a condensation reaction, this is a condensation reaction, and the Brady's reagent, it is that other compound I told you it is very important, and we will use it in the test of carbonyl compounds, 2,4-dinitrophenylhydrazine. Sometimes it is represented like this, 2,4-dinitrophenylhydrazine, DNPH. And then we have a reaction with a ketone and hydrogen cyanide. I want to ask you to also identify the conditions we use here. And finally, we have a compound which is from a terminal alkyne. And number 2, you will write a mechanism for this reaction, reaction number 1 and reaction number 4. The reactions for condensation reaction and mechanism for the nucleophilic addition reactions. That is the end of today's lesson. I thank you for your participation, your attention, and for always being there to follow the TV learning programs. Thank you very much.